Wonderful. Okay, Marc, floor is yours.
Fantastic. Well, thank you so much. This is a real pleasure. Actually, yesterday was a fantastic day, and I'm looking forward to today as well. I'm Marc Bellemare. I'm a research scientist at Google Brain in Montreal, where I lead the reinforcement learning team. I'm also an adjunct professor at McGill University, and I'm affiliated with MILA in Montreal, the Montreal Institute for Learning Algorithms. And so what I'll be telling you about today is some of the research that I've done in the last little while on, I hesitated in the title actually, artificial curiosity, intrinsic motivation. I'd love to hear your thoughts as to what's the appropriate word for this. But before I get started in the main talk, I thought after listening to the talks yesterday, I figured I would do a bit of self-advertisement. And so you might or might not have heard about this. So let me tell you about distributional reinforcement learning. For the last 4 or 5 years now, I've been involved in this line of work called distributional reinforcement learning. And the best way to think about it is that distributional reinforcement learning is to probability distributions, what classical reinforcement learning is to expected rewards. So it's an algebra or a language to think about what it means to, for example, do TD over probability distributions. And some of the nice things that come out of it is that you can now reason about risk, I think, in a nice, concise form. You can think about predicting multiple things in the right language. And what I want to say today is actually we have a book that's in prep where we should be summarizing some of these ideas. So it's I'm learning the hard way that it actually takes longer to work on a big piece of text like this, but hopefully it'll be done sometime in the fall, and you can have a look then. And the other reason for bringing this up is my colleague Will Dabney, actually, who was Andy's PhD student, had a paper come out in Nature earlier last year where they actually looked at recordings of dopaminergic neurons, and please don't quiz me too much on this because I'm not on the paper, but a recording of dopaminergic neurons in experiments where rewards are variable. And effectively, if you do distributional learning, the learning rule will look different at the population level. So different neurons will actually implement different learning rules. And well, they found evidence that this is the case in certain kinds of dopamine neurons. So if you're curious, please go have a look, and we can have a chat. All right, so to actually come to the main point of my talk, I'm very keenly interested in the idea of how to assess the capabilities of different agents, if I can put it this way, right? And so if we look at different biologically intelligent agents, it's clear, for example, that a slug is less capable than a pigeon. And so naturally, the question I think that we want to ask as AI researchers is often, how do we know where our robots fit in that scale of, from slug to virtuoso trombone player, trumpet player, sorry. Well, one way you can do this is you can try to devise benchmarks. So you can try to devise problems for these systems to solve and then see where they go. And so very classically, probably one of the things that have been the most looked at in the whole field of AI is chess, right? And if you could go back in the history of AI research in the 15s and onwards, you can find all kinds of quotes of people arguing effectively that we should use a game like chess to assess intelligence effectively, right? So to assess and evaluate the progress in AI. Allow me, I'll keep going. There's a bunch of pictures on the side that I was trying to get rid of, but I don't have a mouse pointer, so it's quite difficult. So there you go. So, chess is clearly early on, there was this idea that if we understood how to play chess with a computer, we would suddenly be in a much better position to do all the other things that we think intelligence can do. And sort of to be a little tongue-in-cheek here, I wouldn't want to use Deep Blue to drive a self-driving car, right? That's clearly not the right the right continuation to this line of reasoning. But thankfully, chess is not the only game, and it turns out that there are all kinds of games we can use to evaluate intelligence. And if you look back in, again, the history of AI, there's a very long line of AI successes from checkers and chess to Go most recently, and video games and 3D games that did exactly this, that used games to assess the progress of intelligence and measure how complex of a task we could get an AI agent to accomplish. And so that's a subject that's quite dear to my heart, because I do think that games are quite effective at assessing things. The rules are clear, success is clear. It's often games are things that will be recognized by the broader community, so we don't have to explain why this benchmark matters. And so, as a matter of fact, one of the things that I've done that I did during my PhD was to work on what we call the arcade learning environment, which is a platform that allows reinforcement learning agents to interface with the Atari 2600. So you see it in the top left of the screen here. The Atari was released in 1977, and as a platform basically was one of the first consoles where you could plug into your television and then you could play video games through your television. Okay, so on the right-hand side, you have the Atari equivalent of the classic agent environment loop, right? So in Atari, a state, or actually an observation, would be a screen of the game, basically just like a snapshot. And an action is actually a joystick motion. Okay, so up, down, left, right, or the button press. And the rewards we define to be the change in score. So almost all Atari games have a score attached to them, a clear notion of progress again. And so we can define reward to be the score differential, and that provides us with a reward signal. Then we have a full RL environment, and we can operate in this. What's interesting about the Atari is that through the ALE, in fact, specifically, agents can play over 60 games that we can try them on. Okay, so very briefly, the reason why the Atari we thought would be interesting was for a few reasons that we sort of summarize in these three properties here: diverse, interesting, and independent. And so let me go through each of these in turn. Diverse is very simple. The Atari is interesting to assess the progress of AI because there's many different games, very diverse games, that we can try it on, right? So there's not a single benchmark that we're given. Second, those games are also interesting for humans. So they're games, they're benchmarks that people like to play and enjoy watching AI agents play as well. And so this sort of creates intrinsic value in the benchmark itself. The last one, independent, is in some sense the most important from a benchmarking perspective, which is that all of these games were designed in the late 70s to early mid 80s. And they were designed by people who didn't think or didn't have AI in mind when they worked on this. So what that means is that all of these games were designed to be challenging in their own right, and not to demonstrate some specific point about an algorithm, right? So they're free in some sense of researcher bias, and that's really important in a benchmark. All right. So just to give you a feel for why this is an important benchmark, if we compare to previous benchmarks in reinforcement learning, previous systems that we were looking at the time, the Atari had this massive perceptual challenge where the state, the image, is about 33,000 pixels big. And in fact, the agent receives 60, we call these frames, it receives 60 frames per second. And so decisions that effectively need to be made, the base rate is 60 times per second. And a game will last 5 to 30 minutes. So that gives you a feel for the time span that we're talking about here. And so in many respects, one of the biggest challenges was to be able to design an AI agent that could play all Atari games using a common algorithm from these pixels. Okay, and as I'm sure you know, the big success of 2015 for reinforcement learning was these deep Q networks that we published in Nature when I was at DeepMind. And effectively, deep Q network addresses the perceptual intelligence challenge by using deep learning. Okay, so combining a fairly elaborate deep neural network with existing reinforcement learning pieces, with a few new pieces built in, to demonstrate that we could combine the two to address this perceptual challenge. I won't go over the whole architecture here, but what you're seeing here is sort of a bird's eye view of all the pieces that operate inside DQN. There's a replay memory. There's of course, at the core of it, there's a learning algorithm, which is Q learning. There's a replay, as I said, there's a replay network, and then the core is the deep network. And the deep network takes in 4 Atari frames and outputs a Q function, right? So the prediction of the sum of the rewards going forward. So that was a big success. And actually, let me show you very briefly what this looks like if you haven't seen it before. I'm going to play the video now. This is from the original paper. This is a game called Breakout. Breakout is a game where you have a paddle at the beginning. That's the agent is controlling the thing at the bottom, and there's a ball that is bouncing up and down. And the goal of the agent is to, or the player in general, is to try to break as many bricks as possible. So you can see it. I'm sure you can infer the way this game works just by watching it. The agent receives score, in this case, a score differential, every time the ball hits a brick. And then there's 5 lives. So then if you've lost all of your lives, then that's the end of the game. And so this agent is using, this is DQN, it's using a deep network to learn to map images to Q values. And then it's using Q learning to effectively perform credit assignment and decide what is the best course of action, right? And so what you're seeing here, this takes course over multiple games. I think it was 600 that we saw. And you can tell it was pretty exciting at the time, that after a little while of playing, the agent actually becomes what we would call superhuman at this game, where it's better, definitely better than me, for example, at playing Breakout. So this is what you're seeing here is a chart of the 49 games that were assessed in the Nature paper. I said it was 60 games in total. The Nature paper, for various reasons, used 49. 49 games were assessed where we trained the same algorithm, the same DQN on these 49 games for the same amount of time, and then compared its performance to the performance of a human player. Okay, and so you have this line here that says at human level of above. This was a human professional gamer that got to play each game 5 times, and then the score was recorded, averaged, and then some normalization process went on where 0% meant, I believe this was as bad as the random agent, so choosing actions completely at random, and 100% would have been the score of that professional gamer. And 75% was decided as a nice line to draw as where we might expect a regular human to play these games. And this is a fair assessment. In fact, if you look at many of the games that DQN is playing, it is clearly doing something quite elaborate. So you have here in blue is the score of DQN, and gray is actually the score of the agents that I devised during my PhD. And that gives you a feel for these. These scores, of course, are listed in order of performance compared to the human. Okay, so why am I showing you all of this? Well, there's 60 games, as I said, inside the ALE. And if we look at the previous chart and we think about what's going on, we can sort of feel that the games that that DQN is performing best at are these games that have a fairly reactive flavor to them, if you allow me. So at the top left, you see Breakout, which you already saw in a video. Some other examples of reactive games might be Space Invaders, a very classic game, Centipede, or racing games where, for example, you're driving quickly along a road and you have to pass other cars. For these games, the main challenge in many ways is to do credit assignment. to decide on the basis of actions taken, what is the best course of action, right? And this is what many of the tools from reinforcement learning allow us to do, okay? But there's other games inside the ALE that are of a very different flavor. So I'm going to play this video for you. I believe this one doesn't have sound, but if it does, I'm going to warn you, this will be a blast from the past in terms of the sound quality. So let me get started. It does. So I don't know if you can hear it. It's a little garish. So this is a game called Montezuma's Revenge. It was designed in 1983. It seems like my screen froze. I don't know if that's the case. Oh, there we go. Did my screen freeze? I can't tell if that's the case or not.
Yeah, we don't see anything moving, but we hear you fine.
Yeah. And also the nice sounds.
So you can hear the sounds but not see the screen. I think it's the worst of both worlds.
No. I think the screen is fine.
The screen is fine. I'll tell the story and we can come back. So this is a game called Montezuma's Revenge. It was designed in 1983 by a 16-year-old called Robert Yeager. And it's an incredibly challenging game. Actually, this is a game I played when I was a child, and I have very frustrating memories of it. And it's very, very different from Breakout. It's a game where the player controls this little character at the bottom that you saw, and the character, if it makes a mistake, if it falls off the platform, loses a life, always resets at the middle. And the goal of the game, unlike these other games where you have to do something, react to the world, this game asks you to actually pick up a key, open a door, leave the room, go into a different room. Maybe I'll play a bit more of the video and we'll see if that goes, and you can see it go to the other room. I think it's a bandwidth question. Well, and so all in all, this takes place at a much larger time scale than a game like Breakout or Space Invaders. And in fact, we can measure this. So a single playthrough Montezuma's Revenge is probably 10 or 15 minutes at the very least. Okay. So both of these are games from the ALE, but if we actually put them side by side, they look very different, as I said. Okay. And we can actually try to get at the core of what makes them different in terms of the behavior that's required to achieve something. So if you look at Breakout, a small change in behavior changes the pedal, probably whether it hits the ball or doesn't hit the ball, right? And so a small change in behavior will actually have large consequences on the stream of rewards that's to be received, okay? On top of that, rewards are what I might call temporally dense, in the sense that every time you hit the ball and you hit a brick at the top, you receive a reward. So it's there's this trail of breadcrumbs that tells the agent how it should behave in terms of maximizing reward. And last but not least, in some sense, wrong decisions are cheap, because if the agent moves the pedal the wrong way and the ball falls through, that's okay. We just restart where we left off, and there's actually very few consequences. It doesn't take many decisions to come back to that old position. With a game like Montezuma's Revenge, all of these things go away. So for example, failing near the key where you see on the screen right now would reset you at the beginning of the labyrinth, right? So the wrong decision will actually be very costly in terms of progress so far. And some parts of the game, are very sensitive to the choices, and other parts, in fact, are not sensitive at all. So if you're standing on a platform and you take a single one of these actions that are at 60 hertz, 60 times per second, it has absolutely no effect on the game, okay? So all of this to say, there's a term in arcade play called button mashing. You can learn to play Breakout by button mashing, by just pressing buttons at random, but you can't do this with Montezuma's Revenge. Okay. And so in fact, in 2016, we took a closer look at this problem. And one thing we did is we organized games based on the difficulty with which you could learn or not learn them using we call button mesh an epsilon greedy. So an epsilon greedy exploration strategy, right, that chooses actions mostly according to the best current value estimates, and then chooses a proportion of actions at random. And you see the table at the bottom of the screen. On the left-hand side, you have what we call the easy exploration, which were the games where the epsilon greedy strategy will actually get you quite far. Okay, and then the hard exploration games were the games where that was not the case. And even within that hard category, we actually made a further distinction, which was games with dense reward, which means epsilon greedy might not be the right way to play this game. For example, Pac-Man, which you see on the screen here, is an example of this. In Pac-Man, you can collect these little pellets all along the way. You do get points until you get stuck in a corner, and then there's no more points to be collected. And then there was the last category in red with the red square. These were the games where the rewards are sparse and epsilon greedy gets you nowhere. Okay, so 60 games, or in fact, I think 55 in this table, that we've categorized based on their difficulty of exploration. So it turns out that if you go back to the scores produced by DQN, what we find is that actually the overwhelming majority of games at the bottom of that plot are exactly of that category. That is, DQN does really well on games where exploration is not an issue. And the harder, in some sense, the exploration problem, the more difficult, or the more DQN struggles with respect to the human performance. And in fact, there's 3 games from that taxonomy that are not in the DQN table. These are the bottom: Surround, Pitfall, and Solaris. And well, these are all at 0%. So all of these are at the very bottom of that curve. So that's quite telling that maybe solving the problem of perceptual intelligence is an important part in creating an AI agent that can play Atari games, but it's not the only problem. Okay, and to try to explain this, or sort of move to the next slide, the way I think of this is that there's multiple ways to do exploration, and when we think of an AI agent, there's really the credit assignment part, which is what DQN does so well, and there's the exploration part, which is almost orthogonal to the credit assignment question. And so here's 3 different strategies for doing exploration. You could do local exploration, maybe by analogy. If you've ever been to a very crowded place, for me, this is Camden Locks, where I used to live before. You're hungry, you're looking for food. This is a very crowded market. You're moving around, and it's very difficult to find your way around. So you just go, you move around the space at random until you find the thing you're looking for, and then you purchase the food that you need. This is maybe in contrast with, say, if you're at the grocery store, where you might perform much more systematic exploration, where you know that there's aisles, and you can traverse each aisle in turn, looking for the thing that you'd like to purchase. And then there's actually a third kind of exploration, which I'm going to call curiosity-driven exploration here, which is maybe much more like what we would do at the restaurant. I don't systematically explore a restaurant's menu, but rather I'm drawn to specific items of the menu based maybe on interest or curiosity or whatnot. And I think it's important to recognize these different modes of exploration, because they all have their place in designing agents, but they're also very different behaviorally. Okay, so the solution we came up with to deal with the game of Montezuma's Revenge was actually to hark back to information theoretic curiosity, which you'll all be familiar with. So allow me to describe this mathematically here, and then I'll explain a bit the relationship to some of the things that you might be familiar with. So I have a model P, which assigns probabilities to outcomes. And I'm going to look at random outcomes, capital O, that are time indexed. And then there's a realization O, little o, that is what did I observe? And so if you want, you can take this model and then add actions and add states. And so the core of this model, the core of this idea is to define the notion of prediction gain. And prediction gain is, as the equation says, it's the log probability of the outcome being O, given that I've actually already observed an outcome being O, minus the log probability of the outcome being O. So what does that mean? It's the change in log probability of a specific outcome O before and after observing a single instance of that outcome. Okay. And so it turns out that this equation, you can use this equation to relate a number of different formulations of what we might call surprise, or surprisal or Bayesian surprise. So this is all in the 2016 paper, and I'm happy to talk to you more about this or point you towards the right place. But effectively, we talked, for example, yesterday, the difference between the Etienne-Baldi definition and a Schmidt-Huber definition. If you look at prediction gain with the right mathematical model, they're pretty much equivalent. There's some subtle differences, and we can certainly make them different. But at first order approximation, they're all measuring the change in your belief about a certain outcome coming true after observing that outcome. Okay. All right. So now the challenge here is not so much to define this term, but to use it in a fairly large system like the ALE. Okay. And the challenge is that in the ALE, there's 33,000 pixels, and they're all color pixels, and each image is seen once. So now it's almost an epistemic question of what does it mean to assign probability to an item that comes from such a large set. Okay. One solution is to use a probabilistic generative model, right? Something that can generate images and therefore assign a probability to these images. And so that's fine. We can call it a sedensity model. But now the problem is that, in fact, if you look at the probabilities created or assigned by these models, they're incredibly tiny. And so I was actually quite generous here when I said 10 to the minus 100. It's typically more in the 100 for image, a full-size image like this. It would be on the order of 5,000 bits, which would be 2 to the minus 5,000. So clearly, that probability is not something that is really the right scale, the right object. And actually had a fantastic discussion with Tom about this yesterday, and a bit through email as well. So our solution here is to measure model sensitivity by the pseudocount method. And so let me describe this to you very briefly. And it's a very simple trick. Maybe I should stop here and explain this trick. We have a model that gives us probabilities, and it's probabilities over a very large space. In a way that the space, it doesn't make sense to reason about it directly. But we think that the model is calibrated in some sense, in the sense that if we look at how much change has been affected in the model after observing an outcome, it's still meaningful. So this is a simple algebra trick where we're going to, normally what we would do is we define the probability of the outcome in terms of a ratio of counts, right? That's normally the equation goes from left to right. We say the probability of O is a count NO divided by the total count. And that's just the model that we have. Here, what we do is we reverse that relationship. We start with the probability, and then we posit that there exist pseudocounts that actually reflect this probability distribution. And then we do the same thing with the probability after observing the outcome. And then what we say is, well, if that's true, then the counts should have gone up by 1. So we start with 2 values that we know, which are the probabilities on the left-hand side, and 2 unknowns, NO and N total. And then we have 2 equations, 2 unknowns, so we can solve for them and actually extract NO. Okay. And this actually allows us to transform back probabilities into a space that's much more familiar, which is counts. How many times I've actually seen something. And this actually works quite well. So this is it. We'll see if that works again. It's the same thing, but this is, we took this idea and effectively turned these pseudocounts into a artificial curiosity for one of these Atari playing agents, specifically DQN. So let me play it and see as it's playing. I can explain this a little bit. We call this novelty-based rewards at the time. This is the video from 2016. And this is actually the AI agent playing. And you can see that clearly there's behavior that's here that isn't random. And it's hard to know from just seeing the learning. But the point that what I want to show you here is exactly this, that through looking at the behavior of this agent from episode to episode, we really see that it's drawn to novel situations. For example, the first time that it's actually come between two different rooms, it likes to move back and forth around them and discover them. And this time here, it's sort of stuck in that very specific position. These agents tend to be a little obsessive about specific situations. This is also a consequence of how credit assignment is done. So long story short is just by injecting this pseudo count based bonus, we're able, in fact, to recover much of the behavior that we've already seen in more abstract scenarios, right? So where it's effectively lifting many of the ideas from the artificial curiosity research to a much larger space. Okay, so I can see that I'm running short on time, so I'll try to go fast about this. To give you a feel for how this impacted the AI research around the ALE. So here's a timeline. This is actually from some colleagues of mine who were then at Uber AI. You have here, there's a timeline of the scores achieved on Montezuma's Revenge by various, a very large collection, in fact, of algorithms, all built around DQN. Okay, and you can see actually that for a very long time, up to about mid-2016, they were all at 0, and in fact, the first data point above 0 was this method I just presented to you that we call DQN CTS. And this sparked a whole flurry of activity around this, eventually leading, and this is the paper by my colleagues from Uber AI, eventually leading in this algorithm called Go Explore. What's interesting about Go Explore is that it actually combines novelty with systematic exploration. But all this to say that the curiosity was necessary to really crack this problem of getting to play Montezuma's Revenge. So this is pretty exciting. Now, all of this comes with a caveat, and the caveat is that if you look at the amount of time taken to train one of these agents, these are actually amount of real-time play. So 2 days would mean 48 hours of nonstop Atari play. The regime up to DQN was the one set in my PhD, which is about exactly 48 hours of play. And then the Nature paper actually took this to 38 nonstop days of playing, which is a lot of experience for a single agent to go through to learn to play a single game. And so to deal with Montezuma's Revenge in some sense, the research community had to scale this up even further to 202,000 days, to the point where I think you can ask, is curiosity really being used effectively here, or are we resorting back to brute force systematic exploration? But still a pretty exciting achievement. So, so that gives you a feel maybe for what's happened with Montezuma's Revenge. And just to conclude, I started to talk and I talked about this idea of evaluating intelligence. And so if we look at the ALE, there's a whole part of the benchmark, or everything in the benchmark is about perceptual intelligence. But there's clearly also a subset of games that have something more, that require something more of intelligent agents. That's, what I would say is higher level cognitive functions in some sense. And the work we did with curiosity is an attempt at trying to get there. But I don't think we're quite done. And so just to give you a feel for this is a timeline where we've sorted games from the Atari from the release date to basically the first game was released in 1977 to the end in 1989. And I won't spend too much time on the slide since I'm a bit out of time, but what I wanted to point out is that there's a clear progression that the early games made in the 70s are also the games that our agents are good at. And there's a very interesting connection here that many of these games came out of the arcade cabinets, and so were reactive, were designed to be played quickly. You keep putting quarters into it. And the video game community moved and migrated towards more interesting game and more challenging games cognitively as time went on. And we see this in the ALE as well, so that the later games are all the really hard ones in some sense. Okay, and so I won't have time to talk to you about adventure, but just to say that there are some games in the Atari that are so difficult, like adventure like this, that effectively there's no reward until you get to the end. And here you can really ask the question, what would it mean for DQN to play this game? It really isn't the right framework in which to think about learning to play a game like this, if there's absolutely no reward, extrinsic reward given to the agent. So I'm going to wrap up here. Hopefully this made sense. The key question in some sense that I want to bring up today is, do we need to think of curiosity as an intrinsic part of how we should assess, or an intrinsic characteristic that we should assess in intelligent agents? Or what is the behavior that we're seeking to achieve when we talk about curiosity? Okay, so there's clearly certain aspects of domains that we could think about, like open-ended, compositional, that would play a role into this. So on this note, I'm going to just wrap up here and say thank you very much. I think we have maybe a few minutes for questions.
Thank you very much, Marc. Actually, we have a couple of questions because we started 5 minutes with a 5-minute delay. So I like to remind the speakers that you can ask questions right away. You just unmute yourself or you raise your hand and you can ask a question to Marc. Otherwise, we got a lot of questions in the chat. Are there speakers who
It
would
looks
like
like
to?
Jacqueline has a question. Please go ahead.
Hi, Marc. So just a clarification, and maybe I missed something. So you described how you generate the pseudo counts, but I didn't quite get how you get from pseudo counts to novelty-based exploration. Where's that?
I didn't actually describe it. So this is, you're very observant. I realized as I was saying it that I forgot to. So very simple. In fact, we just took the square root inverse of the pseudo count. Really the most naive thing you could do. So 1 over square root of that count. The reason for this was to also connect this to some of the work that's done in theoretical exploration, where they've devised confidence intervals to assess how much we know about these things. In hindsight, I don't think that's actually the best way to use these objects, but it definitely was effective at that time.
So is this, so basically, so the agent is drawn then towards things it hasn't seen before, or it has seen a little bit of. But is this model based in any sense? Because the counts are generated from the probabilities, from the generative model and so on. I don't know, is this?
That's a great question. So the counts are generated by a density model, which, and I've actually struggled to find the biological equivalent of this, to sort of have a good analogy for this. This is a system that knows, that is able to assign a probability to different events. That's really all it's doing. And it's not a Ford model. So it cannot say this is what's going to happen. It can just say this is something that happens frequently, and this is something that doesn't happen very frequently. Now you take this, and to actually achieve this curiosity-driven behavior, you now need to plan with this, right? You now need to sort of plan to return to a position where there was this reward you might want to collect. And the way we did this in the paper is actually we just use replay. So replay will act as a model of sorts, where it allows you to replay trajectories by injecting the reward and changing that reward, the curiosity-driven reward. Then you can actually have the system want to go back somewhere just by virtue of using replay. Does that seem sensible?
Yeah, kind of. Yeah, I think it's good enough for now.
Good enough for now.
I can, yeah.
Okay, maybe we have a question from the audience. There is Dimitri Rodari, and he asked, deep learning algorithms are very good at learning a single task, while the brain is capable to adapt to several situations. So is there a way to extend deep learning techniques to be able to deal with very different tasks?
Right, so that's a very good question. This is actually probably one of the things I'm most interested in, along with curiosity, this idea that we can have representations of tasks. In some sense, to be able to deal with multiple tasks, we need to be able to represent multiple tasks in a common framework. And I think where the deep networks traditionally have failed is that if we learn end-to-end on one task, then we see that the representation they learn of the world is very specific to that system. There's a lot of great work that's been done in trying to address this. I could list a few pieces of work, but I think the jury is still out on how to construct these representations in the right way.
Okay. Yeah,
we have another question by Martin Barry. He asks, in fact, most players, for Atari games at least, never look at the score. I guess he means human players. Would it be possible, or did you try to learn with a curiosity, novelty, surprise-based reward instead of the score that is given in the games?
We did, and I think Deepak actually is going to talk about this as well. But we did actually. So at the end of the 2016 work, we turned off the extrinsic reward, and it turns out that for Montezuma's Revenge, this works just as well. Now, almost. The big difference is that curiosity rewards in our framework are transient. And so they will, as long as they're there, the agent performs well and in fact is motivated to keep progressing through the game. And once these rewards vanish, then all of this goes back and then the agent sits at the beginning being very bored. Yes, so hopefully that answers the question.
Okay, then we got another one by Henrik Mettler. And he asks, do you think that using games as RL benchmarks bears the danger of overfitting RL algorithms or architectures to the constraints of games?
Sure, I can let you finish the question first and then.
Yeah, maybe I repeat the question. Do you think that using games as RL benchmarks bears the danger of overfitting the RL algorithms or architectures to the constraints of games as opposite to real life environments?
That is definitely a danger. And I think that the real world has a lot more to offer than video games or games in general. Our latest project, which we actually published in Nature in December, we worked with a company called Loon to fly balloons in the stratosphere with deep reinforcement learning. And then one of the reasons I was excited about this project was exactly to see what happened if you took these methods outside of the gaming context and try to apply them in a very, very different context.
And may I ask what happened?
Oh, they're flying. So they fly with.
Okay, it worked.
It worked quite well. I think as soon as you move to the real world, you have to deal with the fact that the world is open-ended. There's always external factors that come into play that influence your experiment in a way that if you're in a game, you completely control the environment.
Okay, thank you.
Great. We have another question from the audience if we have a bit more time. So
Yeah, 2 minutes.
Okay, great. So Sandrine asked, and I guess a very related follow-up question, are games indicative enough to assess intelligence, or do we systematically miss important aspects when we only look at these games? So if so, what would other important factors be? Kind of getting back to your balloon paper, as you just mentioned.
I think, yeah, that's, I will say this is, I think there's many people that are better placed to speak of human intelligence than I am. I would imagine that everything that has to do with social intelligence or emotional intelligence, interacting with humans, I think, we are working on AI to interact with humans, but I think we're still quite far from understanding how that works. Mm-hmm. Maybe that's one answer.
Yeah, that sounds great. Thank you.
Okay, I think.
Maybe Andy, that's a question.
Well, so I first want to say this work is great. It's been really instructive to see this work over the years. My question though is, are in any of these games, is it difficult to define what the objective is? They seem, it may be a characteristic of games is that the objective is quite clear. There's a score. Maybe it is only accrued at the end of the game, but I think in a number of tasks, maybe the Loon task, yep. Well, the designer's objective may not be easily determined.
That's totally true. And so there are no games in the Atari, to answer the question, that don't have this property. In fact, we had a procedure. We said the reward is the score differential, and then we found our way around this. In many ways, and I didn't have the chance to touch on this, but this is what I'm most excited about, is to try to answer this question. What would it mean to have a benchmark in which there is no obvious objective assessment? And I actually really like, the monkey room experiments that you looked at a while ago. I really like this from that perspective of saying, what happens if there is no objective, but we still think there's intelligence to be assessed? How would we assess it? What would that mean? How do we assign a numeric score to it? Because if we can't, then it's challenging to even just write a paper about it.
Great, thanks. Yes, I think that's an important challenge.
Okay, thanks once more, Marc. Thank you very much.
Thank you so much. And Jacqueline, I feel like I owe you an answer still, but we can take this offline.
Okay, yeah, thanks, quite. So let's move